All right, so the title of the notes is Introduction to Logarithms. That's what we're doing today. Have any of you guys ever heard of logs? So logarithm is the whole word. Most people don't say logarithm, they just say log. And before we talk about actual logs, I want to give you guys the reason like why we're doing it in this unit. Like why did we do exponential functions for 2 days and then completely switch to logs? So if you guys remember what inverses are, or inverse operations, can you guys remind me what some inverses are? Yeah, multiplication and division. Adding and subtracting. Yeah, taking something and squaring it or square rooting it. What are some other inverses? Yeah, cube and cube root, fourth and fourth root. So those are different inverses that we have worked with in the past. The reason that we're learning about logarithms now is because logarithms are actually inverses of exponential functions. So if you guys remember, inverse operations are operations that undo each other. So if you've multiplied by 2 and you want to undo that, you just divide by 2. Over here, if we have like x to the second power and we want to solve for x, we're going to square root it. That's how we get the x alone. So logarithms are how you deal with problems that are exponential, where we have y equals some base to the exponent of x. And this time, I don't want to square root this. I don't want to x root this because that gets rid of the exponent. I want to get rid of the b so I can solve for the exponent. So this is a little bit different. It's not typical exponents where we have a number there and we can just root it. We have to do a logarithm because that allows us to get the x alone, not get rid of the x. We just want it to be alone. So the way that we do that, a lot of people call this process different things. I've heard scorpion, I've heard cloud, I've heard Tootsie Roll. None of those words mean anything. It's just what helps you to remember. I like Tootsie Roll because I think it's fun and you can start to dance like Leah's doing because there's a song. So the way it works is you take the base and the base of the exponent becomes the base of the log. So we're going to write log base b, and you can see the base of the log is a little subscript. It's like an exponent, but it's below. So log base b, and that's when we Tootsie Roll. Log base b of y equals x. And so once we put it into the log form, the x is now isolated. And if we had numbers for the b and for the y, we could solve for x and actually know what the answer was. So anytime we have something in exponential form and we want to undo it so we can solve for an exponent, we turn it into log form. Anytime we've got like a y value right here that we want to solve for in a log form and we want to get rid of the log, we turn it into exponential form to get rid of the log so we can actually complete the problem. So this is our newest type of inverse operations that we learn about in Math 3 and we haven't learned about before. So now if the teacher asks what are some inverses, you're going to say multiply, divide, add, subtract, square, square root, and then exponents and logs. That's going to be your newest inverse. It's like a normal thing for us to try. So we're going to do a few examples of this. We're going to make sure we know how to say it out loud. So I shouldn't hear anyone say log by equals x because that's not very accurate. We're going to say log base b of y equals x. That's how we read it out loud. Log base b of y equals x. Yeah, no, log base b of y. So, and there's a few numbers that the b value can't equal, and there's a few numbers that the y value can't equal. So we're going to say that the base cannot be 1 because 1 is not a very exciting base, since 1 to any exponent is still just 1. So we're not going to let that happen. We're also going to say that the base has to be greater than 0. So you're not going to have any negative bases. You can have fractions, but you can't have any negatives. The other rule we're going to say is that the y value, so this is called the argument of the log. I'm not going to call it the argument ever again. I'm just going to say the number you're taking the log of. But the argument of the log has to be greater than 0. And the reason for that is because if you take a base and you raise it to a positive number, it just becomes a big positive number. If you take a base and you raise it to 0, what does that give you if you raise something to 0? 1. And if you take a base and you raise it to a negative number, then what does it become? A fraction. So there's no possible way for me to plug an exponent in and get anything other than a positive whole number. Or I guess I could get a fraction here. But there's no way for me to get 0 there. There's no way for me to get a negative there. It has to be a positive number. So that means that when we convert it into log form, this number right here has to be positive. Has to be greater than 0. That makes sense? Right? So the only time you're going to get a no solution problem with logs is if they try to make you take the log of a negative, and if that happens, you're going to say no solution because it's not possible. All right, so we're going to look at just a couple examples of converting back and forth between the two different forms. So exponential form and log form. So when we do these problems, we always start with the base. So can you tell what the base of this problem is? 2. So the base of the log becomes the base of the exponent. Right? So 2, and then when we Tootsie Roll, we go to the other side of the equal sign. So 2 to the third equals 8. And then to check to make sure you did it right, you just want to make sure that that's true. So is it true that 2 to the third power is 8? Yes. All right, for this one, we're going to say 4 to the 0 equals 1, and we want to switch that into the log form. So I'm going to write the word log. What's the base? 4. So the base of the exponent becomes the base of the log. And then we do the Tootsie Roll. And the Tootsie Roll has you go to the opposite side of the equal sign. So log base 4 of 1 equals 0. So this next one we're going to do 1 equals log base 12 of 12. So you can see I switched the order. So what do I start with? The base. The base becomes the base. And then how do I know where to go when I Tootsie Roll? The other side of the equal sign. So 12 to the 1, that means we're going backwards this time. 12 to the 1 equals 12. And is that true? So this time we're going to say 4 equals 1/4 to the negative 1 power. So when I put that into log form, I'm going to write log of 1/4. Good. So the base becomes the base. Log base 1/4 of 4 equals negative 1. So for this one, we're going to do negative 5 equals log base 1/2 of 32. To the -5th equals 32. And make sure anytime you take a fraction and you're raising it to an exponent, that fraction needs to be in parentheses. Okay, we're going to do one more like this just to make sure we got it. I think we do. Alright, so go ahead and write this one on your own. See what you get. Don't say it out loud, just write it on your own. We're doing 81 equals 3 to the 4th. Anyone want to share what they got? Yep. Log base 3 of 81 equals 4. Alright, so that's how we convert back and forth between the two. There's a couple more things that we're going to be doing today. One of those is evaluating logs. We're going to do it first without a calculator, and then we're going to do it with a calculator. So, we're going to do a couple more examples here. Evaluate the log without a calculator. So the first problem is log base 4 of 64. And they want us to say what that equals. So I don't know about you, but even though I know that the converting back and forth is not too hard, for me when I look at logs, I just can't think in terms of them. It's hard for me to think that way. So instead of thinking of this in terms of a log, I'm going to say that if I was to do the Tootsie Roll and think about what this would be in exponential form, my brain works better that way. So I'm going to think of this as 4 to some exponent equals 64. So 4 to some exponent equals 64. 4 to the... Yeah, so you could say 4 to the x equals 64. And then what exponent would give us the right answer? 3. So 4 to the 3rd equals 64. So when I evaluate this, I get 3. So if you don't have your chart out, you might grab it. Your chart is still going to be helpful today. So on this one, we're going to think 2 to some exponent equals 1/16. 2 to some exponent equals 1/16. What do you say?
So 2 to
Negative 4? So 2 to some exponent equals 1/16. And if you check your chart, you notice that if you look in the 2's column, it's the exponent of negative 4 that would do that for you.
Wait, so...
Oh, because it's another one too. It's also 4.
It's also, you can also look in the 4's column. However, this one specifically had a base of 2, so we had to look in the 2's column. So 2 to the negative 4 equals 1/16. Alright, we're going to look at one that's a little bit trickier. Log base 36 of 6, and we want to see what this one is. The reason this one is trickier is because it's not one you can just do in your head, like we kind of did the last ones in our head a little bit. They were pretty straightforward. So for this one, we're going to say 36 to some exponent equals 6. So 36 to some exponent equals 6. And this right here is not easy to solve just by looking at it. This is actually just like a warm-up problem. So this is where we want to look at the chart. We want to see where 36 and 6 show up in the same column. And we want to rewrite them. They show up in the 6's column.
Oh, can I say that?
So,
Can I say what I think it is?
what do you think it is?
Is it -2?
It is not negative 2. So 36 would be 6 to the second, to the x. And then 6 is 6 to the first. So this is 6 to the 2x equals 6 to the 1. And that gives us 2x equals 1. And so x equals 1/2. Now, we can't say x equals 1/2, circle that, call that our answer, because there was no place in the problem where they ever introduced an x. They never put an x in their problem. They never said solve for x. They said to evaluate this. So we just said our x equals 1/2. That means our evaluation is 1/2. So I'm not going to circle x equals 1/2 as my answer.
Oh.
That was me adding some notation into the problem so I had something to solve for. Okay.
It's close.
One more example, we're going to do the same thing. So we're going to do log base 1/3 of 27, and we want to see what that equals. Log base 1/3 of 27. So we're going to say 1/3 to some exponent equals 27. So 1/3 to an exponent equals 27. It's in the 3's column. 3 to the -1 and 3 to the 3rd. So that's 3 to the -x. That's 3 to the 3rd. -x equals 3. So x equals -3. So this is not our answer. We go back up here and we say log base 1/3 of 27 equals -3. How do we feel about evaluating without a calculator?
Easy.
So what's the trick to evaluating without a calculator?
Think of it as like the exponent.
Yeah. Think of it as if you're converting it to the other form. Most of us are pretty good about thinking in terms of exponents, especially now that we have that chart. So if we convert it into a form that we're more comfortable with, then it'll be easier to solve it, basically. All right, we've got two like vocabulary type words in regards to this, and one of them is called the common log, and one of them is called the natural log. All right. Do not write this part on your paper. I'm going to write this off to the side of mine. You do not need to write it. I'm just going to give you a context for what they're talking about here. So if we were solving an equation like x squared equals 25, I would square root each side and I would write it like this, right? I would write the square root like that. If I had x to the third equals 125, what type of root would I be using to get rid of a third as an exponent? A cube root. And how would I write that? Yeah, you put a little 3 with your square root. What if I had an x to the fourth and I was getting rid of the 4? I put a little 4 there. What about if I was doing a fifth root? Put a little 5. Now, the square root is the weird one, right? Because it doesn't have a number there. If it had a number, what would we put? 2. Do you guys know why we don't put a 2 there? It's the most common one, and we're lazy. That's the only reason. So when you look at these 3rd root, 4th root, 5th root, you don't see those a lot. That's why you actually put the number there, because they're not as common. Square roots, we don't put the 2 there because it's the most common thing. You see the same thing with exponents. When do you ever see a person write an exponent of 1? They don't, but literally every number you can think of always has an exponent of 1. The reason we don't write it is because we're lazy. We don't want to write a 1. We don't want to write 5 to the 1, x to the 1, y to the 1. Every time we try to write 5xy. Does that make sense? Yeah, so the common log is the same sort of thing. We have a logarithm that has a base, and it's the most common one. And because we're lazy, anytime we see this, we're actually not going to write the base. We're going to ditch it and just say that's the most common logarithm. That's the one that we assume it is. So the common log is log base 10. And you are very rarely going to see it written that way. You are always going to see it written as log. People generally don't put the base 10 on it. And the reason they do that is because it is the most common one. You don't put the 10 because you see it all the time. And it's annoying to write 10. Because 10 to the first power, 10 to the second power, 10 to the third power, in our numeric culture, we do things in sets of 10. So that's why. Like even our decimals, 0.1 is 1/10, 0.01 is 1/100, that sort of thing. Now if you look at your calculator, what button do you see your calculator has? It has a log button. This is not a log base 2 button, this is not a log base 5 button, this is a log base 10. And log base 10 is the only type of log that it will do. It won't do any other logs, it will only do log base 10. Right? Does that make sense? Yeah. Okay. So let's say we were doing a problem like log of 1,000, and I wanted you to evaluate it without a calculator. What could you do to make that problem a little bit easier on yourself? You can't just take away zeros. Think about how we did the other ones.
Turn into exponent?
Yeah, I would turn it into exponential form. So I would say, all right, remember self, I can't see a 10 there, but there really is a 10 there. I'd put a little 10 there. And then I'd say 10 to some exponent equals 1,000. So 10 to some exponent equals 1,000. 10 to the third. You just count the zeros. So 10 to the 1 is 10. 10 to the 2 is 100. 10 to the 3 is 1,000. Yes. We'll just change that. Yeah. All right. The next one is the natural log. And this is log base E. Have you guys ever seen the little E before?
Yeah.
2.7.
Yeah, that's good. E is a number that was named after, I don't remember his first name, but his last name is Euler. It's E-U-L-E-R. It's just pronounced Euler. So E is Euler's number. It's 2.71 something, something, something. Log base E is the natural log. And this is the one that is weird because when we shortcut this one, we don't actually use the word log. We write ln. Yeah. Natural log. That's what ln is. I'm guessing it's actually the letters L and N because natural log in Latin probably sounds similar to natural log in English, I'm guessing. But ln, and if you notice, underneath the log button there's an ln button on your calculator, so we can also do ln's pretty easily.
Wow.
Okay. Yeah.
Why wouldn't it be an L?
I'm not sure.
It's Spanish.
I'm guessing in Latin it's probably the log word would come first, the natural word would come after it. Most of the number words like historically come from Latin stuff, so. Yeah, but. So if we had a problem like ln of e to the 7th and we wanted to evaluate that, this one is a little bit trickier. For us to evaluate this one by hand, I would take the ln and I would rewrite it as log base e. So this is actually log base e of e to the 7th. And I would do that because at this point I can convert it into the exponential notation rather easily. So I'm saying e to some exponent equals e to the 7th. So e to some exponent equals e to the 7th. Yeah, it's just 7. So ln of e to the 7th equals 7.
Couldn't you just leave the exponent of 7 and just say
Yeah, and once students have worked with these long enough, they start to say that ln and e cancel each other out. Ln and e are opposites of each other, they're inverses, right? Because we're saying that logarithms and exponents are inverses of each other, and so they'd say, yep, those cancel out, 7 is your answer. And we'll get there. I don't want to like start to throw out these things that don't make sense on the first day. So today we're going to focus on doing Tootsie Roll to switch things around and make sure that we understand that, and then we'll start to talk about like, oh, this we can cancel things out certain ways. All right? Okay.
Renee, can I use your paper?
I passed my house the other day. All the way to where it should be. I was so confused.
What'd you say? What'd you say?
I wasn't taking a picture of past.
All right. So you need your calculator in front of you. We are going to be evaluating logs using calculators. So for this one, it says log 53. There is not a base written down. That means I can just use my log button. So I'm going to go ahead and hit the log button. 53. 1.724. I'm going to go ahead and put my little squiggly equal sign. Does anyone remember what that means?
Just about.
Yeah, it means about. It means approximately. It means I'm rounded.
Oh, yeah, you're right.
All right, the next one is going to be ln of 13. So I'm going to click my ln button. So if it's just a log or just an ln, pretty straightforward. Those are easy to do. All right, for this last one, we're going to do log base 3 of 16, and I'm going to show you two different ways to do this problem. So one way is if you're using a school calculator or you already own a TI-84. This is if you use a more recent calculator. If you have a recent one, you can hit the math button and then hit the up arrow twice. And it lets you plug in a log with any base. So this is, you hit the math button, you do up arrow twice, you type it in the way it looks on your paper, and you get that it is approximately 2.524. The other way to type this in, and I'm going to make every single one of you do it, even if you don't have an old calculator, is called the change of base formula. And the reason I want all of you guys to do it is because on the SAT or the ACT, if they do logarithms, it would not surprise me if they had these on a calculator inactive section, where you could not use a calculator, and they wanted you to say like what the equivalent of this was. So change of base can be written two ways. You're manipulating it so that you can plug it into your calculator without having the special functions that new calculators have. This is how people did it in the day when the TIs were a little bit newer and everybody had a TI-83, because TI-83s do not have the ability to do what we just did. So change of base is if you were to write this problem as log of 16 divided by log of 3. That's one way to type it. The other way is to write ln of 16 divided by ln of 3. And I would not be surprised to see that as an SAT question or an ACT question or something like that, where they asked you to do a problem with logs and the answer looked like this rather than the answer actually being a decimal. Kind of them getting at, like, do you actually understand how to work with logs? So you can type it in either way. Log 16 divided by log 3. ln 16 divided by ln 3. And you'll notice that either way you do it, you get the same decimal that you got when you typed it in exactly the way it looked on your paper. So that's a valid way to do it. If you have an older calculator, you're going to have to do it this way all the time. Yes?
So, why do you do
The proof behind this is not as simple as just saying this is how it works. The way that I remember it is I just remember the 16 is above the 3, so I do 16 divided by 3. That's how I think of it. But as far as like where it comes from, I'd have to look it up and get back to you. I don't remember off the top of my head.
No, okay, that makes sense.
All right. So I'm going to give you guys a sheet to practice that. So here's what I want. On the left column, I want you guys, especially if you have a newer calculator, I want you to do the option where you hit the math button, go up twice, and you plug it in exactly the way it looks. Okay? So for all the odds, we're going to write math, hit the up arrow twice, plug it in exactly the way it looks. For the even problems, I want you to do change of base if necessary, and I want you to write down how you changed it before you plugged it in your calculator. So for number 2, I don't need to do a change of base for that one because that's just the common log, and I can just hit log 7.89, and I'm all good on that one. I can get that answer. Number 4 is the same way. I can just plug in log 3.2, get that answer. But for number 6, I would have to do the change of base. So there are 2 options for how you can write your answer for number 6. You could write log of 4.9 divided by log of 6, or you could write ln of 4.9 divided by ln of 6. Those are the only 2 options you have, and then I want you to actually plug it in that way and tell me what the answer is. I want you to be able to do it both ways, and again, the reason for that is SAT, ACT if you don't have a calculator to use, or if you're ever stuck in a situation where you have to use a TI-83 because you left your calculator at home, and that's all they have available to you, okay? So on the left side, you can do the shortcut. On the right side, you're going to do the change of base for any of the ones that don't have a log base 10 or a log base 10. Okay? Do you understand what we're doing? So we're going to type like the wind because you have 5 minutes, and we'll see. Hopefully, we can get a lot of these done in 5 minutes.